All right. Hi, everyone. I had a lot of questions regarding number 7 from the multiple choice on the test. This is the question number 7. The correct answer is E. So again, if f is differentiable, tells us f is continuous. So from continuity, we have those things absolutely have to be true. Differentiability just tells us that the derivative exists at those spots. If I look at this piece, that's the definition of f prime of 3 equaling 5. And I look at this piece, that's the other way we can write the derivative of f at 3, which is not this one. So note that this is 5 is f prime of 3. So if this were true, what it would be saying is that every differentiable function has a continuous derivative. This is the definition of continuity for the derivative. And that doesn't have to be true. Every differentiable function does not have to have a continuous derivative. And the place that I think the place that we're getting confused on is that the limit of the derivative is not necessarily going to be the same as the derivative. So let me give you an example. So let's say we have the piecewise function x squared times sine 1 over x for whenever x is not 0, and then 0 when it is. So let me first show you that this is a continuous function. So if I look at the left-hand limit of f of x, that's going to be the limit as x approaches 0 from the left of x squared times the limit as x approaches 0 from the left of sine 1 over x. Now, the limit as x approaches 0 from the left of x squared, I can just do a substitution and get 0 squared. And the limit as x approaches 0 from the left, if I plug 0 in for x, I have 1 over 0, which is infinity. And sine of infinity is indeterminate, right? Or undefined, does not exist because we're oscillating between 0 or between -1 and +1. But that's okay, right? If we're just have something that's in between -1 and +1, if I multiply whatever that number is by 0, it's still 0. So we're good there. And the limit as x approaches from the right of f of x, well, it's the exact same argument, right? The only thing that changes is that, these guys are plus signs, but everything else still holds. So we're good there. And then f of 0, well, it's defined as 0 in the piecewise. So we're good there. So we have continuity. Now what I want to do is I want to show you that f is still differentiable at 0. So if I want to calculate f prime of 0 for a piecewise function like this, where, like the 0 is a standalone, what I'm going to do is I'm going to do my limit definition. So I'm going to take the limit as h approaches 0 of f of x plus h minus, I should say, not f of x, f of 0 plus h minus f of 0 all over h. So when I do that, I have 0 plus h squared times sine of 1 over 0 plus h minus 0 squared times sine of 1 over 0 all over h. Now sine 0 squared times sine of 1 over 0, we've dealt with that already. That's just 0. So the rest of this simplifies to be h squared sine of h, or 1 over h. So the 0 minus 0 doesn't really matter. I reduce that. So I have the limit as h approaches 0 of just h sine 1 over h, which again, same issue that we saw back here. We know that's just 0. So we know f is differentiable at 0, specifically that f prime of 0 is equal to 0. Now what I'll do is I'll show you it's not continuous at x equals 0, that f prime won't be continuous. So to do that, I'll find the derivative of f prime. So to do that, I'm just going to take the derivative of the first piece of my piecewise function. Note, to do that, I need to do a product rule to start. So I'll have x squared times the derivative of sine 1 over x plus sine 1 over x times the derivative of x squared. And to do the derivative of sine 1 over x, I need to use the chain rule. So I have x squared times cosine 1 over x times x to the negative, should be negative x to the negative 2. Like that. And then plus 2x sine 1 over x. And that's for x not equal to 0, and still 0 when x is equal to 0, because we showed right here that the derivative at 0 is equal to 0. So we can fill that in. Okay? So if I look at the limit as x approaches 0 from the left of the derivative, I'm going to get the limit as x approaches 0 from the left of cosine 1 over x plus 2x sine 1 over x. So I can distribute that limit across and pull the constant of 2 out front. This, again, what we're seeing is just going to be 0. We've done that a couple of times now. But here, cosine of 1 over x is basically the limit as, or what's happening to cosine at infinity. And again, one of these trig functions, if you go to infinity, it's just oscillating back and forth between 0 and 1, and because it's standing by itself, it does not exist. So if the limit as x approaches 0 from the left does not exist, we know that that cannot equal f prime of 0. So we've shown that f prime is not continuous at x equals 0, or in other words, the limit as x approaches 0 of f prime of x does not equal 0, because it does not exist. Now, that's a pretty nasty example. It took me a minute to cook something up where we would get a differentiable function that was discontinuous. Like that's not something you're really going to run into. But the idea here is that just because a function is differentiable does not guarantee that the derivative is going to be continuous. And I know that we've gotten a little bit lax in looking at, the limit as like x approaches 0 from the left of f prime of x, and saying that that is like the same thing as the limit as h approaches 0 from the left of like f of x plus h minus f of x all over h. Those two things are not necessarily the same. My example here being here that my left-hand limit, or so this is telling us that the limit as x approaches 0 of f prime of x doesn't exist, because if the left hand and right hand line, if either the left or right doesn't exist, the limit can't exist. But notice that this isn't the same result as this. So that can happen. It's rare that it happens. I had to cook up a really, kind of obscure piecewise example for that to happen. But that's what's going on. Just to kind of illustrate visually what's really happening here. If we look at x squared times sine 1 over x, right? That was our original f of x for everywhere not 0. And I'll just go from like negative 2 pi to 2 pi. And we'll go from like negative 20 to 20 or something. I don't really know for the y's, but that should be okay. I'll make that scale like pi over 2. I don't think it really will matter though. Oops. So just take a look at, I'm in degree mode, aren't I? As soon as I didn't see a picture coming in, I knew. Okay. So if I look, everything looks okay, but if we zoom in real close, let's go like negative 1 to 1 or something. So everything seems fine, but boy, that flattened out a lot there. Let's zoom in a little more. Pick something that's a little bit easier to see. If I zoom in a lot, oops. I screwed something up there, didn't I? Yeah, I put those in the wrong spot. Whatever, that doesn't matter. This is what I wanted to be negative 0.01. Okay. And whoa, I'm getting crazy like oscillating behaviors. We're getting close to 0 here. So we're not actually settling down to 0. So this is what that function kind of looks like. That x squared sine 1 over x, and when we're getting really close to 0, it's going cuckoo crazy. And it's just too rough for the derivative to exist there at 0. If it's a nice smooth curve, then this relationship is going to hold. But if you have something that's real rough, like this guy is, these two things will cease to be equal. But again, like in practice, you wouldn't really see that. The point of this question is just realizing that this statement here at the bottom is saying that f prime is continuous, which doesn't have to be true. You can have a continuous function that's differentiable, and the derivative doesn't need to be continuous. And our example here is this piecewise that I just gave you.